This video is part of a series about how to compute and visualize three-dimensional minimum spanning trees. This particular video will go over some of the things that I've learned about using the CGAL library, Computational Geometry Algorithms Library. The particular example that I'll be doing here will be to compute the Delaunay triangulation of three-dimensional points. Why would you want to do this? In school, many of us learned how to compute the minimum spanning trees off of a graph. If you have a set of three-dimensional points, you first need to have that graph to compute the minimum spanning tree on. Now you could just use a complete graph. Every point is connected to every other point. However, if you have a large number of points, the n-squared nature of the complete algorithm makes for a very large problem, hence the Delaunay triangulation. It has been shown that using the Delaunay triangulation as the basis of minimum spanning tree will give you the optimal result. So let's get into how to use the CGAL library and some of the things that I have learned. To generate a Delaunay triangulation, I've used the CGAL library. All of the code in this series of videos can be found on my GitHub, and I'll have a link to that in the description below. So let's first talk about how to generate a triangulation of a bunch of points. So in the data here, I have included pointers to the relevant online documentation. One of the problems with CGAL is that because it has many templated data structures, that means that Doxygen can be confused and not have pointers when you would like them. Hopefully the pointers that I'm giving here will be sufficient. So first, when talking about CGAL, we need to talk about floating point numbers. Floating point numbers, as you multiply divide, round errors can mean that 2 points that are sort of in the same place kind of are not. With CGAL, the first thing you need to do is tell it how to deal with floating point math. To be exact here means that as it's doing math internally, 2 points that are multiplied divided will be handled more symbolically such that the points that were equal before continue to be equal. Inexact coordinates means that as you're loading it from somewhere else, you can do a little bit of fuzzing there. So here we have the type for this set of floating point math into K. Then what we want is to say, okay, we're going to do a three-dimensional Delaunay triangulation using the type of floating point math that we have specified up here above. And then here we'll need a typedef for the type of point structure that is used within the triangulation. So in this example, I have VTK files that are of the format that PairView likes to read. And I find that it's helpful to be able to read that same file both into PairView as well as into the boost graph algorithms that I'll talk about in a separate video. So for that, I have this read VTK function, which takes two functions: how to add a vertex to the triangulation and how to add an edge to the triangulation. So in this case, or how to add an edge to the data. Now in this case, I don't need to add edges because CGAL does that, but later on for the boost graph stuff, I will need to do that. To add a point to the Delaunay triangulation is actually pretty easy. Once I have the X, Y, and Z of my vertex, I simply create a point and then insert that into the triangulation. Okay, that's how things are loaded. So here in my main file, in my main function, I will create a structure of triangulation type. At first, they will have no vertices. I will then call the read VTK function that I spoke of earlier, for which the add vertex and add edge needed to be defined. Once things are loaded into the triangulation is done. As you add one edge, it will adjust the triangulation. It is an incremental update. After that, I simply will then need to generate a new VTK file that indicates all of the triangulation lines. So as I explained in my PairView video, I have a simple header. We're going to create a polydata dataset. We have a number of points. Then we have a number of points in the triangulation. Now, one thing to be aware of here is that there are two sets of points that you can get from the triangulation. One of them includes an infinite vertex that is used as part of the computation. And because of that, we need to use the finite vertices iterators here. Okay, so now let's actually iterate through each of the vertices and print them out into our output. Right? So we have simple iterator here that starts with finite vertices begin, goes to finite vertices end, prints them out. Do the same thing with number of finite edges. Finite edges begin, finite edges end. Now we show the lines that we will have coming out of this triangulation. So again, with the VTK format lines, how many lines are you going to give and how many numbers do you need to give to represent those? Here it's 3 because first you need to say I have 2 points followed by the 2 points. Iterate, finite edges begin, finite edges end. It's looks a little bit involved to actually get the points out, because in the triangulation, the vertices or the edges are not directly represented as edges. The triangulation is represented as faces, and from those faces you need to get the edges. So from the iterator, we say here we have an edge. First you need to figure out which cell, which face is that edge a part of, and then see, since a face, 3 points, we need to know which of the indices in those 3 are we talking about. So then we say, okay, well, we want the first, second, or third vertex of the face. And then once we have that vertex handle, we can get an actual point from it. And then here, first, second, or third other vertex of that face, get the point from it. So now we know the XYZ coordinates of the to and from point, the source and destination of each of the line that we're looking at right now. Here, we need to go up to the earlier code a little bit. Here I'm creating a lookup table that can then be used as part of the VTK file. Now, if you recall, the VTK file first is a list of points, numbered 0 through n, and then the edges tell you it's the 5th vertex connected to the 10th vertex. Then you have the 11th vertex connected to the 238th vertex. So in that interest, we need to create a mapping from XYZ point into the index of the VTK file. So that's what I do here. I have a map from point to int. As I go through the vertices, I add that point to the mapping, and I'll simply say, well, the size of the current mapping is going to then be the index. As I add one by one, that size will go up. I need this -1 here because I am inserting the point into the map first, and then I assign it. So the size has already been adjusted by the time this computation is done. All right, so then I print out my VTK line. I have 2 points. I have the first index, and then I have the second index. Once I do that, I have an output file that gives me my Delaunay triangulation.